Hello and welcome to another video. In this video, we will see about the proportional, integral, and derivative controller. Suppose we have a system with a transfer function of 100 divided by 2s plus 1. And the system is controlled by a controller. This controller can be proportional, integral, or proportional integral derivative. Proportional means proportional to the error. So this will just be a gain. Okay. So here let me take with gain 1. So this is our output and we are giving a feedback. So this is the input. So WFS is the input which is given to a comparator, and this difference between the input and the output. So the output is fed back from here, and the difference between WFS and YFS, WFS and YFS, that is the error. So this error is getting multiplied with the proportional controller. Here the proportional gain is 1. So that is used to control the process. Now suppose you have a disturbance. Disturbance is some element which doesn't have any control. So it will be added here. So the disturbance transfer function can be written here. So let that be 3 by 2s plus 1. So there is some disturbance z of s added here. Now suppose this is our system. So we have a process, we have a proportional controller, we have a disturbance, and now we need to find how this affects, how this proportional controller will help us maintain this output. So when WFS is equal to 0, how this disturbance affects our output. So how the ratio between the disturbance and the output. Sorry. Transfer function between y of s and z of s when w of s is equal to 0. When there is no input, when there is nothing given here as input, provided w of s is 0. So how to find y of s by z of s? So I am rearranging this same block diagram in a different way. Z of s 3 by 2s plus 1. So that is being added here. And this entire feedback loop is given here. Since there is no input, you can take that negative, this negative here multiplied with 1, that is written here, minus 1, and the transfer function 100 by 2s plus 1, that is being added. So this is the restructured block diagram. Now how to get the transfer function here? So this part can be reduced as g of s by 1 minus g of s h of s. It is 1 minus since we have a positive sign here. So g of s is 1 and h of s is minus 100 by 2s plus 1. So it will be 1 plus 100 by 2s plus 1. When we reduce this, we will rearrange it and reduce it. We will get as 2s plus 1 divided by 2s plus 101. So that part is in series with 3 by 2s plus 1. So we will just multiply 3 by 2s plus 1, which results in 3 by 2s plus 101. So this is our final transfer function, reduced transfer function between our disturbance and the output. So what we got is z of s, y of s divided by z of s. Now suppose you are giving a step input to this disturbance. What happens to the output? For final value theorem, final value theorem will help us identify what happens to the output as time tends to infinity. So limit s tends to 0, s into our function. Now here we have limit s tends to 0, s into, we are giving a step input to the transfer function 3 by 2s plus 0. So that results in 3 by 101, which is approximately 0.0297. So when we give a step input, it initially deviates too much and then settles finally at some error value of 0.297, 0.0297. So this is the output, response to the output. This error difference will be 0.0297. So this is how we identify the final value of the due to the disturbance input. So now we have some transfer function 3 by 2s plus 1, which is the reduced transfer function between the disturbance and the output. So when we give a step input to the disturbance, how the output changes and what is the final value of the output. So this is the final value of the output. So thank you.